Welcome back, everybody, to another edition of No Here, No Problem. Today, we're going to be working on an objective that is, to some people, they really dislike it. To some, they really like it. I don't know. Personally, I like it, but it's challenging because it requires a little bit of reading. But it's easy. Problems are fairly easy. But we are officially in December. I thought I'd wear my Grinch hat here, just because we're approaching the holidays. But I just thought it'd be a little humorous, maybe a little Grinch. All right, anyways, let's get started though. So we're gonna be talking about today about probability, and so let me go ahead and shrink myself down here so I am out of the way. If I can get the thing to work here. Oh my gosh, that's not working. There we go. All right, let's shrunk down and get me as small as possible. Get me out of the way. All right, so here we go. Sorry, technical problems. So with probability, what we're talking about is fractions and percentages, and we're talking about the chances of things actually happening versus not happening. And so the probability of an event, before we actually dive into these problems, we have to know the lingo a little bit. That when we talk about any happening whose result is uncertain, we call it an experiment. And so the results of the experiments are called outcomes. And then the sample space is all of the possible outcomes that can take place. And all the little parts of the sample space are known as events. So, for instance, when I roll a six-sided dice, okay, the sample space is all of the numbers, all of them from 1 to 6. But for the outcomes, we're talking about, side 1, side 2, side 3, side 4, and so on and so forth, okay? So that's the difference as far as lingos when we're talking about things. Let's dive into some sample space stuff. All right. You have to be able to create sample spaces or at least visualize them. So this is a classic one where we talk about flipping a coin. Sometimes you might see flipping a coin and rolling a dice. In this one, we say we flip a coin. Well, a coin, if we flip it, you can go ahead and flip it, it's got one of two things that can happen. It could either be heads or tails. Okay. So the events here are that it's heads or tails. We've got either heads or we've got tails taking place. These are the events. Okay. When two coins are flipped, what are the possible outcomes? Well, if I flip heads on the first shot, the next round I can then flip heads, heads, or I can go heads and then I can go tails. So as far as the possible outcomes go, we would have heads, heads, or heads, tails. Okay. Now, I could have gone tails on the first round, and what would happen is I would flip it again, and we would go tails, heads, and then we can go tails and then tails. So the total possible outcomes here would be tails, heads, and then tails, tails. So there's 4 total outcomes in the sample space. If I was to say what's the probability of getting heads, heads, you would see that there's 1 out of 4. If I said what's the probability of getting tails, you would see it's 1 out of 4. If I say what's the probability, of getting a heads and a tails, or I'm sorry, a heads or a tails, you would see in this case that there's 2 out of 4. Okay. If we go one step further and we say, let's go ahead and generate when we have 3 flips taking place. Well, if I go heads and then heads on the first 2, the next time I would flip it, I would also get heads and heads, or heads or tails. So that means I can go heads, heads, heads. I can go heads, heads, tails. These are possible outcomes that we can have here. So we can have heads, 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 tails. That's 2. I'm sorry, of the possible outcomes there. Let's go for the next one. Ready? I can have heads, tails, heads. I can do heads, tails, tails. So let's write down those possible outcomes. Heads, tails, heads, heads, tails, tails. Okay, so that's 2 more outcomes there. Let's go on to the next one. This one we've got where we go tails, heads, heads, and then we've got tails, heads, tails. So let's write those out. We've got heads. I'm sorry, whoops, we're on tails now. So we're going to do tails, heads, heads, tails, heads, tails. And then we've got one more possible outcome here that could take place. We've got tails, tails, heads, and then we've got tails, tails, tails. So what would those look like? We're going to have tails, tails, heads, tails, tails, tails. So in this case, we could see that there's 8 possible outcomes here. Now, if we apply the fundamental counting principle, here's what we know. There's 3 flips taking place. On the first flip, there's 2 possible ways it can go, heads or tails. On the second flip, there's 2 possible ways that this can go, heads or tails. And on the third one, there's only 2 possible ways it can go, which is heads or tails. And if we take and multiply all these events together, we get that there's a total of 8 possible events that could take place. Okay? Or I'm sorry, 8 possible outcomes. If I was to say, what's the probability of there being all of the flips being heads, you would see that there's only 1 out of the 8. All right? So the probability of event, I've already been mentioning a little bit, is the probability of an event taking place out of an entire sample space. The one thing that we really have to know here that's very important for this is that all events, every one of the events will always add up to 100% when we put all of the possible outcomes together. So if we go back to here and I think about the scenario where I said, what's the probability of being heads? Let's say probability of heads, heads, heads. You would say that it is 1 out of 8. Well, what's the probability of at least 1 tails taking place? Every other scenario here, every other scenario has at least 1 tails. We've got where there's 1 tail here and 1 tail here. There's 1 tail here, there's 2 tails here, and so on and so forth. We can say there's 3. So ultimately what ends up happening is that there's 7 out of 8. And if we take these and add them together, 1 out of 8 and 7 out of 8 is going to add up to 8 out of 8, which is 1. Or we can even say that this is 12.5% chance. And then the other one is going to be 87.5% chance. Okay, and together those add up to 100%. Okay. All right, so let's look at probabilities in another example. If we have 2 coins that are tossed, what's the probability that both lands heads up? Okay, so when we're looking at this, we're saying we're only going to look at 2 flips, not 3. So we're going to focus on this. And what's the probability that it ends up being heads, heads? Well, we go heads, heads. There's 1 outcome. And then we can see that there are combined others. We got 2, 3, 4. So there's 4 possible outcomes here, which we just worked on. And there is only a 1 out of 4 chance of me getting heads, heads on it. Okay. For part B, a card is drawn at random. Now, I put a deck of cards in here because I'm fairly confident not everybody has ever seen a deck of cards. People don't play it like they used to. But when you look at a deck of cards, there's 52 cards total in this. There are 4 of any kind of card. So in this case, there's 4 aces. There's 4 2s, 3s, 4, 5, 6, 7, 8, 9, 10. 4 of every card. These cards right here are known as jacks. These are known as queens. And these are known as kings. Okay. When we look at the names of them, what the suits are, this one right here is called a club. This one is called a spade. Like when you dig, it's called a spade. Obviously, this one is called a heart. And this one is called a diamond. So when we say a card is drawn at random from a standard deck of playing cards, what's the probability that it's an ace? Well, the probability of there being an ace out of the total is that when we look at this, there are 4 aces in here. You can see those 4 right there. And there is 4 out of 52, which means there is a 1 out of 13 chance. Okay? And that means that my other chance, I have a 12 out of 13 chance of picking anything that's not an ace. All right? All right, so I just said the probability of getting heads is 1 out of 4. Probability of picking the card is going to be 4 out of 52 or 1 out of 13. So what do we mean when we talk about probability and we mean mutually exclusive events? Well, mutually exclusive events are events that have no outcomes in common whatsoever. Okay? When they have no intersection whatsoever. So, for instance, when we say we take 2 dice and they're going to be tossed. So I toss a dice, the event A rolls a sum of 6, and then in another event that has no relation to the other one, I'm going to go ahead and roll and get a sum of 9. These are called mutually exclusive. They have no bearing on each other. So when it says to find the probability of one or the other of two mutually exclusive events will occur, you can add their individual probabilities. So probability A plus probability B minus, and I'm going to read this again here, probability of the first event, probability of the second event, take away the probability of an overlap that's taking place in the event. I'll show you an example of this that makes a little more sense visually, okay? And then in probability of A and probability B, those are mutually exclusive. One has nothing to do with the other. So I'll give you an example of that as well, okay? So let's look at a standard deck of playing cards. If I was to say to you, the probability of drawing an ace or an 8, okay? These are mutually exclusive because I'm going to reach in the deck, I'm going to draw a card, and one has nothing to do with the other, right? So if I draw an ace, there's 4 out of 52 cards that are aces, okay? And then the 8s, there are 8 out of, what am I saying? There's 4 out of 52 cards that are 8s. So the probability of me drawing an ace or an 8 is 8 out of 52, which if I reduce this is going to be 2 out of 13, okay? So I have 2 out of 13 chance of picking either an ace or an 8 if I was to draw one card from the pile. Now, these are called mutually exclusive events because there's no overlap between them. What about when I have an event where there actually is overlap? So in this example, we're going to say, what's the probability of drawing a heart? Okay. Well, when we look at the probability of drawing a heart, we can see that there's hearts right here. And how many hearts are there in this deck? Well, I'm going to color this in so we can actually see this, that there are 13 total cards in here, okay? And actually, I have a really good way to make this work, to pop for us. What I'm going to do is I'm going to actually highlight this so it's actually yellow. Okay, you'll see why in a second. And so I'm going to highlight all this, make sure it's all really nice and yellow. There we go, okay? And then we're going to say, what's the probability of drawing a heart? Well, when we look at this, we can see that there is a 13 out of 52 chance of drawing a heart. What's the probability of drawing a face card? Okay. Well, when I draw the face cards and look at this, we're going to do this one in blue. These are all my face cards right here. Okay. And you can see total in this that there are a total of 12 out of 52 that are face cards. Okay. Now, normally I would just add these together and we would just go ahead and say that there's 25 out of 52, but there's an overlap that takes place. These 3 cards, which are green because yellow and blue make green, these 3 cards were counted not once but twice. So they were hearts and they were face cards. This is what we call an intersection between the two. And when this intersection takes place, we're going to subtract that intersection, which is those 3 out of the 52, because I counted them more than once. All right. So when we have 25 out of 52 plus 3, we're going to have 28 out of 52, which then if I reduce that is going to be 14 out of 26. 20, I just want to make sure I put the right number here because it's late and I am tired. But you have a 7 out of 13 chance of picking either a heart or a face card, okay? All right, so 2 independent events. Now, this is my favorite one. Hands down, this is my favorite one. I'm going to show you why in a second here. But these are independent events that literally have no bearing on each other. If I roll a dice and then I roll a dice again, that first roll has literally nothing to do with the second one. And these are called independent events. And when we're talking about this, we're saying that we're going to take and multiply the events together. Now, I love doing this. I love this example here because in the real world, people try to make money off of this on a game called roulette. So if you look at a roulette table, there's red and black, and then there's these actual colors of green that are mixed in there. And people love to do this because it's like a 50-50 chance, like flipping a coin, except for those green ones that are on there, those throw everything off as far as the stats go. But people are like, all right, I'm going to put money down on black. And if it comes up black, I'm going to start making some strategies, get superstitious, right? So here's what happens here. They start off, it comes up black. They went ahead and put a $5 bet on it and they win and they've got money. Yay. Okay. Well, then it comes up black again. And in their mind, they went ahead and bet on black again. I'm sorry, it didn't come up black. They bet black again. This time it came up red. So they lose money. So they're like, all right, I'm going to just stick with it. I'm just going to stick with it. So then they could bet on it again, black, and it comes up black. They make some money. Then it comes up, then they bet black again. It comes up black. So they make some money. So they're like, okay, the strategy's working. I'm going to go ahead and keep betting black. So then they bet black. Oh no, red comes up. They lose their money. I'm going to bet black again. Black comes up. Yeah, I win money. I'm going to bet black again. Oh no, it came up red. I lost money. And now in their mind, they're thinking, I'm going to go ahead and start betting the other direction because look at how many times it's come up black. It's black numerous times. Black, 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 black. It's got to come up red now. So they bet red. It comes up black. They lose money. So they're like, oh, it can't come up black again. I'm just going to stick with red. They bet red. It comes up black. They lose money. They bet red. It comes black. They lose money. They bet red, and then they actually hit. They win their money back on that. And they're like, okay, they bet red. It comes up black. They're like, oh God. All right, I'm gonna go ahead and switch. I'm gonna go back to black. So then they go ahead. They bet black. They win black. And you can see what happens here. There's a psychological thing that starts to take place. People look at this, they think that there's patterns going on. Yes, there's patterns that you could see, but the probabilities are independent of each other. There's a 50-50 of it coming up black. The next spin, there's 50-50 of it coming up black. The next spin, there's 50-50 of it coming up black. One has nothing to do with the other. So if I was to say, what's the probability of coming up red? And then the probability of coming up black. Okay, and then the probability of coming up red. Here's what would happen. It's a half. Now we're going to ignore the greens. The greens skew this, but for the sake of just this, we'll say you have a half a chance red, half a chance black, half a chance red. You have a 1 out of 8 chance of actually having this exact scenario come up, right? Well, what's the probability of it coming up black, and then coming up black, and then coming up black? Guess what? You have a 1/2, 1/2, 1/2. You have a 1 out of 8 chance of it coming up that way too. So people don't know what they're doing. They just throw down money, and a lot of people lose money very quickly on roulette. So let me show you an example of random integers generated on a computer, and we're talking about multiple events taking place where one has nothing to do with the other. So we have this computer that's going to randomly generate an integer. The first integer is going to come up. It's going to have to be from a 1 to a 5, okay? The probability of that happening is that there is 1, 2, 3, 4, 5, right? So there's 5 out of all 20 numbers, which reduces to 1/4. The probability of it coming up one of those numbers, and then another one of those, and then another one of those, each one has nothing to do with the previous. And so because of that, we say that they're independent. We multiply the probabilities together. So there's a 1/4 chance, a 1/4 chance, and then a 1/4 chance. We have a 1/4 times 1/4 times 1/4. This is a 1 out of 64 chance. That's it. So take these properties, try applying them to the problems. Pay attention to the fact that we're talking about the part out of the total, and that all percentages and all probabilities should always add up to 1, okay? You've got this. Be safe, be responsible, be respectful. Don't forget to like and subscribe. Have a wonderful day.